Yeah, you might have noticed from my title it was a lot of different things to cover, and I'll cover most of them in a little detail, but some I've focused on some aspects more than others. So I changed the title to Future Pathways of Climate Change. So I just actually wanted to start with some history. I assume actually Steve probably covered a bit of this history, but I just wanted to put the context of climate change in this historical perspective. And you probably know that John Tyndall was the first to really say that, identify that greenhouse gases like CO2 could affect the climate. And I think Steve probably went through that in a detailed way. But yeah, so this was 150 years ago. He had this public demonstration where he was able to demonstrate that CO2 and other greenhouse gases, water vapour, could impact, could trap heat. But for those of you who don't know, there was also recently discovered that a female scientist had also talked about this a few years before him. So go girls. So Tyndall sort of identified that, and he was a really famous chemist at the time. There's a mountain in Tasmania named after him. But it wasn't really tied to climate and climate change until a lot later. And so these are some of the scientists that started to link the greenhouse gases and the climate and CO2 to climate change. And I won't go through the numbers because I know we're short of time, but I just wanted to say that most of them sort of made an estimate that is pretty close to what we still know today of CO2's impact on temperature, about 3 degrees Celsius, best estimate. And it wasn't until Sawyer in 1972 that he actually made a prediction of, okay, if we keep increasing CO2 at this rate, we'll get this increase of 0.6 degrees centigrade by the end of the 20th century, and that's about what happened. As you can see here. So they were all making the predictions of temperature change when there wasn't really global warming to speak of. But yeah, Sawyer's prediction in the early 70s was pretty much spot on to what happened. So that's just a bit of historical context, but I guess so we've identified that we know CO2 affects the climate, but of course that physical climate stuff that we're talking about is only that blue box at the top. And there's all these other things that can impact the climate, and these interactions between the human and the Earth systems are what our community and other communities are really grappling with right now. So there's a lot of things to think about. There's all the scenarios, trying to come up with ideas of what the future drivers of the climate will be, how that will have impacts, and then what we do with it, how we decide to respond to that. So we could just say nothing, we won't do anything, we'll just live with it. We could mitigate, so that's trying to stop emitting greenhouse gases. We could accept that we'll have to adapt, so there's a lot of work looking at that. And then there's all these kind of economic and social questions that come up when you start thinking about this problem. So I'll touch a little bit on geoengineering at the end as a mechanism for responding to climate change. So I guess we've established that CO2 increase leads to warming, but that doesn't get us very far. If it's only going to warm another 0.2 degrees, then who cares? If it's only going to warm for another 10 years, who cares, right? So I guess the outline of my talk is how big is the warming, and so we'll go through a bit of a back of an envelope calculation of climate sensitivity, sort of in the spirit of your super problems. I'll talk quite a bit about scenarios and how they're developed. Then how long will it warm, and that's where we'll talk a lot about commitment, how much climate change we are committed to and how that's different across different variables. How confident are we, which talks about the uncertainty in the projections, and then what should we do about it. So quickly go through mitigation, adaptation and geoengineering. So this is the back of the envelope calculation for climate sensitivity. So climate sensitivity is this formal definition is this change in annual mean global surface temperature due to a doubling of CO2. And that's at equilibrium, so once all those long feedbacks and the warming in the ocean has sort of stabilised. And in the IPCC, this is estimated from a variety of sources, from models, from observed warming, and from paleoclimate. And as you probably know, this estimate has changed very little in the past 40 years, and it's been a real focus of climate scientists to try and narrow that range so that we can give better projections of what's going to happen in the future. So it's likely to be that range. So can we estimate it how do we estimate it from the observed temperature record? So this is global temperatures from 1840 up to present, and the CO2 is from Law Dome in Antarctica, and you can see the CO2 going up. And this red line is from Mauna Loa in Hawaii, measuring CO2, and then the black is the temperatures, I think, from surface thermometers. So you can see that we've increased CO2 by about 20% since 1970, but there's also other greenhouse gases that have increased, so I think about 30% increase in sort of equivalent CO2, warmed about 0.6 degrees centigrade, which is what we talked about earlier with John Sawyer. And so you can just basically come up with an estimate of climate sensitivity of the increase in temperature divided by the increase in CO2, and you get 2 degrees. So I think that's nice. But of course, this may be an underestimate because this is actually a transient climate sensitivity estimate. So all of the warming hasn't actually happened in this way of calculating it. There's also other things that might offset the warming, but I think this is a nice way of just saying you can get a fairly quick estimate. And this is the figure from IPCC that goes through all these different ways of estimating the climate sensitivity, and that they came up with this range. So paleoclimate, instrumental, lots of different ways of trying to constrain it from what we know about the observations. And they come up with this 1.5 to 4.5, I think, degrees Celsius for a doubling of CO2. So I'm going to talk about how climate will change in the future, and from more of a, I guess you've been looking at the response of the Earth system this week from a lot of the lectures. I'm going to talk about the scenarios. So the future climate depends on these social and economic choices, also the response of the Earth system, which is the climate sensitivity, but also inherent variability. So yeah, we don't have this crystal ball, unfortunately. We don't know how our population is going to change. We don't know what energy use we're going to choose. And so the community since, I guess, about in the mid-90s has been using this scenario approach. And they're designed to span lots of different potential pathways. We're not actually going to follow any of them, but the idea is to come up with all the range of plausible pathways for the future. So in the IPCC latest report, probably know these scenarios are called the representative concentration pathways. And so this process was, for the first time, all the social economic modelers got together with the climate scientists and designed these scenarios together. Whereas previously the socio-economic modelers would come up with some ideas of where they thought GDP and population was going to go. They'd give that to the climate models. They'd come up with the forcings, the greenhouse gases, and then we'd run the climate models. And that process would take 3 to 4 years, and we just couldn't update it quick enough. So now they all get together, usually in Aspen in August, and they come up with these scenarios together. So you don't need to know the details of this, but I guess the idea is that there's sort of these range of future emissions that then the socio-economic people can go and come up with lots of different storylines of how those emissions can be achieved. And then the climate scientists go and we run our models and look at the climate impacts. And so I think this is nice because it means that there's a lot of interdisciplinary kind of interaction and a lot of different questions can be asked if we're doing this together. So these were the four scenarios that were chosen for IPCC, or for AR5. And these are the fossil fuel emissions over time, so from 1850 up to 2100. And so they have a historical simulation, and then you can see the various pathways that were investigated. So RCP 2.6 is this one here, where emissions have to peak in 2020, so pretty soon. And then we actually need to have negative emissions by the end of the century, so that requires technology that's not actually available right now, but I guess it's an optimistic scenario that humans will be able to develop that technology and be able to scale it up so it can have an important effect. And then there were two sort of mid-range scenarios, and then RCP 8.5, which was more of a business as usual scenario. So they're the emissions, and I just want to highlight that what actually affects the climate is not the emissions, but it's the concentration, so the amount of CO2 in the atmosphere after it's all, you've got rid of all the uptake from the land and the ocean, so the land that Andy talked about. So the actual amount of CO2 concentrations in the atmosphere, and that they have similar spread, but you can see that the changes aren't, you're not going down below zero here. You've still got a lot of CO2 in the atmosphere, even in RCP 2.6. So you can decline. And that's important when we get onto this commitment part later in the talk. And so these scenarios also at 2100, they are designed to stabilise these ones so that you have constant sort of forcing for 200 years. And some models looked at these, and I think there's a lot more interesting work that could be done trying to understand the responses over centennial timescales. So for CMIP 6, so the next IPCC report, they met in Aspen in 2013 and came up with some new scenarios. So unfortunately, our models are going to be different and our scenarios are going to be different again, but they're fairly similar to the previous RCP. So these are called shared socio-economic pathways, and this diagram is, these papers are actually really dense and hard to actually work out how it's done, but they basically come up with now storylines of different sort of human development in the future, and then both go away and come up with different scenarios for the climate and also different human development. So these are the ones that have been chosen. So there's different storylines of how humans will develop over the coming century. These ones are the optimistic ones. They're going to have good improvements in health and energy efficiency. There's some that are less optimistic, lots of regional rivalry. Everyone will focus only in their country or national interests, inequality. So they're these socio-economic pathways, and then the climate forcing here. So you could imagine all of these boxes being filled with different scenarios, and of course we can't run 30 scenarios with our climate models, so they've picked out these 4 in the dark blue that are going to be run. So it's similar, RCP 2.6, this will be very similar, the SSP 1-2.6, I think. Again, a stabilisation in the middle. This one's a bit higher than RCP 2.6, it's now 7. But they're designed to try and be similar to the RCPs in terms of radiative forcing. And just wanted to highlight that the choice of these was to try and improve on some issues that were identified in the RCP. So particularly with aerosols, it was determined that there wasn't enough spread in the aerosols in the coming century. They were all declining too rapidly. So now this SSP 3-7 will have aerosols kind of staying high aerosol emissions before declining later. So that gives us a bit more spread in the climate response that we might expect. So that's the way that I guess the climate science community is trying to look at how big is the warming, how big will the warming be over the next century, and that's a combination of how the models, or how the climate will respond, and also the radiative forcing due to the socio-economic choices. Then if you want to ask how long will it warm for, we get into something called commitment. So I guess I wanted to break it up with a bit quick quiz. So if CO2 emissions went to zero today, which is one form of, one way of thinking about how much more warming we're committed to, how long would climate change persist? Anyone wanting to yell out? Yep.
Hundreds of thousands of years.
Hundreds of thousands. Any other?
Just saying it's fine.
3 months.
Like, are you just looking at temperature or also sea level rise?
Yeah, I guess this is broadly framed as climate change.
Centuries.
Centuries.
Centuries. Yep. You're much more educated than my first years.
Depends what you're looking at. Ocean acidification, right? The carbon's in the ocean. It's not coming out of the system. That's hundreds of thousands of years.
Oh, so ocean acidification,
Yeah, like
as
that.
opposed to
I
actually
guess.
physical climate change, temperature.
Yeah, I guess you're talking about temperature.
Yeah, no, I mean, I figured you guys would all know this, so that's good. So there are various definitions of climate commitment, and so these were the ones that were discussed in the latest IPCC report. So there's zero emissions, when you basically stop emitting any greenhouse gases or any human emissions, aerosols included at present. And you get a bit of, this is global surface warming on the x-axis and time on the y. So you get a bit of a kick due to no longer having aerosols cooling the climate. You get a bit of warming initially and then it starts declining. So at the moment we're emitting, I think, at twice the rate of CO2 that's being uptaken by the climate system, by the ocean and by the land. So if we want to actually get to this constant forcing, which is this one, where you have CO2 concentrations stable, then we'd need to immediately halve the emissions right now to get to this. Zero emissions would eventually lead to cooling of the climate. And then if we just have constant emissions, then we get this sort of warming. So yeah, you can also think of it in terms of the socio-economic commitment, like how quickly could we decarbonise, and that leads to definitely at least 1.5 degrees warming above pre-industrial. So that ends up being similar to this constant forcing scenario. So, but that's a really optimistic. That's the sort of RCP 2.6 kind of scenario, which is going to be tricky to implement. So we're definitely committed to a fair bit of warming, no matter what radical things we do. And so you can think of this in terms of this constant forcing, stable CO2 concentration here. And a lot of studies have been done to see how much warming that will have, and most models tend to get another 0.5 degree, 0.6 degrees Celsius warming by over the next 100 century years. If you look at the zero emissions commitment, where you just suddenly decrease emissions here, and this is again over time, so these are carbon emissions, and you can decrease them, say, at this yellow line, or the orange or the red. You do get stable temperatures fairly quickly, but it does depend on where you decide to go to zero. So the amount of warming still to come in the system is dependent on how much we've warmed already. And it doesn't decrease very quickly. So the warming stabilises at the level of where you stopped. And this is the temperatures here. So I guess the main point is that about 15 to 40% of the emitted carbon remains in the atmosphere for 1,000 years at least. So there's a lot of carbon in the atmosphere that will it doesn't get removed quickly. That's why it's this is a really tricky problem. It doesn't get rained out. It just stays in the atmosphere for a long time. So if you really want to actually reverse climate change, you have to think of negative emissions. There we go. And then I guess, yeah, if you're thinking about sea level change, so the temperatures stabilise, and this is from a paper we had in 2012, but the sea level just keeps going for centuries and centuries. So this is the sea level rise only from thermal expansion. So John Church was talking also about the sea level rise from glaciers as well. That's not included in this, but you can see for these different RCPs, so high mitigation up to business as usual, you will get additional sea level rise up these simulations around to 2300. The upper ocean does start stabilise in the lower emission scenarios, but the upper 3 kilometres are still continuing to warm over these next 300 years. So we are committed to climate change, even if global temperatures stabilise, the sea level is still going to keep going. And then if you're thinking about more of the patterns of warming, like Dietmar was talking about, a difference between the stabilisation, these equilibrium warming, you can really see the difference in the Southern Ocean. So this is temperature change at 2100 for a middle of the road scenario. And you can see it's warmed over the Arctic and land, like Dietmar was showing, but not as sort of a minimum in the Southern Ocean. And I think someone asked the question, I don't know if Leila answered it, that it's because the ocean has a really deep mixed layer that the Southern Ocean is able to take up a lot of the heat and keep the SSTs quite relatively cool. But eventually the heat is all taken up and the Southern Ocean warms. You can see that up here, the difference is really highlighted in the Southern Ocean. And you can think of how that might then impact other variables like rainfall and circulation once you have that equilibrium in. So I just pulled out this paper from quite a while ago by Chai, CSIRO, looking at the implications for future climate change down in the centuries. And this is a stabilisation run, I think at 2100 it was stabilised, so here, and then run for another 300 years. So you can see the SSTs, as we've shown, stabilise quite quickly. Something like the southern annular mode, which is really dependent on the gradients between the tropics and the poles. As we've seen in the observations and in the climate models, we get this increase in the southern annular mode. It's one of a really robust change. And this is just sort of, you can think of it as the position of the westerly winds in the Southern Ocean. So they move forward, which is identified by the SAM going positive. But once the SST stabilise, the SAM does come back to where it was. So the winds move back equatorly. But you can see there's studies that link this trend in the SAM to decline in rainfall in southwest Western Australia. You can see that it takes 300 years before it gets back to where it had started from. So there's long kind of delays in the system, even if the global temperatures spring back quite quickly. This is just one model, so who knows how right it is, but just wanted to make the point that there's a lot of commitment in the climate system across lots of different variables. So the other thing that was a new finding in the IPCC report was that the amount of emissions that you've had historically are linearly related to the temperature increase. So it doesn't matter when you've emitted the CO2, whether you emit a lot now and then less later, it's the total amount that's important. So this is trying to have a bit of a cartoon from that. So from these zero emission scenarios, these idealized scenarios that we came up with, you can see that the warming indicated here falls along this line of how much you've emitted. You get this warming sort of a linear relationship. And so this is where the point is that it doesn't matter, the timing of it doesn't matter. So you can have a lot of emissions in the next 20 years, but then you have to reduce to very low or negative emissions later in the century. But as far as the temperature increase is concerned, it doesn't matter if you've done that or whether you've just kind of decreased earlier and have more emissions later. So that was a very important kind of message that came out of IPCC, the fifth assessment report, because it means that for whatever temperature target that the world's decided to take, it only matters how much total emissions is burned, and so it really then hands it over to the policy people to decide how to divvy up the amount of emissions that we've got left. And so this was the iconic figure, which is not easy to interpret, but basically it's the same thing. Everything's lining up on this line. If you include non-CO2 greenhouse gases, it's this steepness. If you're only looking at CO2, then it's this steepness. And so there's different lines depending on the different, whether you include sort of methane and other and aerosols in the relationships. But basically, if you want to stick to under 2 degrees, which is what the world has agreed in the Paris Agreement, to try and stick below 2 degrees warming above pre-industrial. If you're only thinking in terms of CO2, then you need to be here, because we want to be in this plume, this grey plume, we want to be in the likely range, so a third from the edge. So that means we've got 1,000 gigatons of carbon left to burn, or total to burn. We've already emitted 531, that's now a bit outdated. If you actually include the other non-CO2 emissions, then we've actually got even less. We've got, I think it was 780 or something total emissions to burn. And so you can see that there's not much left if we want to try and stick below 2 degrees. And then you can use this relationship to think about different climate targets that you might want to go aim for. So the most recent, the Paris Agreement agreed to try and aim to having 1.5 degrees of total climate change above pre-industrial. But this also doesn't include things like thawing permafrost that is, with low confidence, assessed to be another 50 to 250 gigatons of carbon that might be released by the end of the 21st century. So it's kind of highlighting we're running out of time. So just to summarise that, basically every tonne of CO2 causes about the same amount of warming, no matter when and where it's emitted. If we want to limit warming to likely less than 2 degrees, then we have to limit it to 1,000 gigatons. If you want to account for other non-CO2 forcings, such as aerosols, then you've only got 800 left, and then there's just throwing this in here quickly, some colleagues recently had a paper looking at how the Trump administration might impact these future scenarios too. So climate and integrated assessment modelling, people are trying to come up with some new scenarios to figure out how delays in the US has now pulled out of the Paris Agreement, how that might then affect our ability to stick to this 2 degree target. And they basically they look at delays due to lack of input, sort of research into new technologies and other things, and conclude that we probably aren't going to make the pass. So just wanted to highlight these nice ways of also visualising if you're ever talking to people about this carbon budget and global temperature relationship. This is this spiral, which you've probably all seen, was originally developed by Ed Hawkins at Reading University in the UK. Apparently this was played on the Rio Olympics opening ceremony. It's famous. And then Malte Meinshausen and his group at this Climate Energy College in Melbourne did this carbon budget one where you can basically, it's the doomsday clock, I guess, isn't it? So how close are we to running up to this 1.5 degree target? And I think this is the 2 degree. You can really see, this is nice, you can see the acceleration in this warming. This is how much of the pie we've got left. Okay, so we've come up with we've covered how big is the warming, talked about these idealized scenarios of how long it will continue to warm. And then I guess the next thing is how confident are we in those? So I won't talk about this very much, but just wanted to highlight some sources of uncertainty in the projections. So I think Steve would have talked a lot about the clouds and the different feedbacks that are our main sources of scientific uncertainty. There's also these, what John Church was talking about, the ice dynamics and these sort of long time scale feedbacks that we don't even have included in our models. So they're the things that affect climate sensitivity or the response of the Earth to future scenarios of greenhouse gas increases. There's also a lot of uncertainty, or different uncertainty depending on what variable you're looking at. So temperature is more credible than rainfall, for instance, and averages are more reliable than extremes. And then it's also the geographical scale of what you're interested in. So if you're averaging over a large scale, you've got more confidence in that than if you're averaging or just wanting to look at Sydney, for instance. And then the internal variability of the climate system can matter if you're looking in the near term. And then, of course, there's the uncertainty from which pathway we're going to follow, whether we're going to have a high mitigation scenario or a business as usual scenario. So these are just some nice figures that tried to summarise that. This is, again, by Ed Hawkins. And so this is from time on the x-axis. And it's basically the fraction of the total uncertainty compared to code. And this is in sort of, from decade timescales. So you can see, if you're interested in the global temperature change, the main uncertainty in the next few decades is really coming from the model response. So we don't know how the Earth is going to respond to the climate change. But if you're looking at the end of the century, then it's really the difference in the scenarios that's the main source of uncertainty. The orange is the internal variability, so things like the AMO that Leila just talked about, or the PDO, how they might sort of influence decadal variability in global temperatures. Also has a big influence in the next few decades, but then is really not that important if you're looking at climate change at the end of the century. If you look now at Australia, you can see that internal variability has a lot larger role, but still by the end of the century it's really the scenarios that are important. If you're looking then at rainfall instead, it's really the models that are dominating the uncertainty in what's going to happen. So basically we don't know well enough all the processes that are important for how rainfall will respond to climate change. And so there's a broad spread in the model projections for that. Whereas the scenario spread is not as large. And then again, if you're looking at Australia, a smaller region, then internal variability of the climate systems, due to El Nino and other just natural climate variability, is really a dominant source of uncertainty for the next certainly 50 years, and even it's still fairly large at the end of the century. So then the last question is, what should we do about it? So as I said at the beginning, we've identified that we have a problem. We've identified that probably a large problem, that it's going to be quite a large amount of warming that will impact lots of ecosystems and other things. We've identified that it's going to be in the system for a long time. We're committed to a certain amount of warming no matter what we do. So there's 3 pathways, or 4 if you decide to ignore it. That's one option. We can mitigate, which is what the scenarios have been trying to show, different pathways of mitigation and how they'll affect the climate. We'll have to adapt because we're definitely likely to have at least another ½ degree of warming over the next century, no matter what we do. And then the third option is geoengineering. So, do people know much about geoengineering? Yeah, so I guess one way of highlighting mitigation versus adaptation is to look at the global temperature change. The increasing scenarios of CO2, so this is up CP 2.6 up to 8.5, and this is the temperature change centred on 2025 compared to present day. So you can see, and then this is the temperature change at the end of the 21st century compared to present day. So you can see if you're going down in the near-term projections, it doesn't really matter which pathway we follow. The warming that we're going to have we're already committed to. It's already based on emissions that are in the system and that the climate system is just trying to catch up to. But if you're thinking about the end of the 21st century, then it's really scenario dependent, and so mitigation can influence the outcome. And then the third option is geoengineering, and so this is a formal definition of geoengineering, and it's been talked about a lot in the last decade. There's a whole MIP, Model Intercomparison Project, called Geoengineering that is looking at different geoengineering scenarios and how they'll affect the climate. So for an action to be geoengineering, the environmental change must be the primary goal rather than a side effect. So you have to be doing it with a purpose. And the intent and effect of the manipulation must be large in scale. So it can't just be cloud seeding in Queensland, it has to be continental to global. So there's 2 groups of geoengineering approaches. The first one is carbon dioxide removal. So they're trying to basically vacuum the CO2 out of the atmosphere. So basically trying to reverse the amount of CO2 we've put into the atmosphere by pulling it out. And it's subtle, but it's different to mitigation. Mitigation is trying to stop the emissions getting up there in the first place. And so this is more the vacuum cleaner scenario. And then the second approach is solar radiation management. And so that's where you're trying to reduce solar radiation received by the Earth by deflecting sunlight or increasing the reflectivity of the Earth system. So the second one is the one that's being most studied at the moment. But there are also some studies looking at this and its impact on climate. So this is just a schematic of where in the energy budget these are trying to solve the problem. So the solar radiation management is basically trying to reflect the incoming sunlight before it gets into the Earth system, whereas the carbon dioxide removal is basically trying to remove some of the CO2 so that it's not trapping as much heat. And so this is a nice little figure talking about all various different examples of geoengineering. So there's ones that are trying to suck it, pump it down into the ocean or into land. Cloud seeding is one example where you shoot aerosols into the clouds to help brighten them and reflect more sunlight that way. This one, aerosols in the stratosphere, so you're basically injecting aerosols up high into the atmosphere where they're really stable and will stay for a long time, or for a few years. Or you could put giant mirrors in the stratosphere, or you can think of it as like a big umbrella, just trying to stop the sunlight getting in. These are sort of the various ways you could think of doing carbon dioxide removal. So you can enhance the land carbon sinks by planting lots of trees. You can burn biomass and turn it into charcoal and then bury it in the ground so that it's then it's biomass that's already pulled out the carbon from the atmosphere. But then there's studies that saying you'd have to plant about half of the UK to actually have any significant effect. So that has to be really large scale, and it's probably unrealistic to grow biomass just for the purpose of carbon sequestration. Weathering, capture from the air, the giant vacuum, and then ocean fertilisation is one that's had a bit of attention. So you basically throw nitrogen or iron into the iron filings into the ocean, and that then enhances the oceanic uptake of CO2. So this is that one where you dump the iron in. It causes algae to bloom, phytoplankton, that then sequesters that CO2, takes up more CO2, and then dies off and sinks to the ocean floor where it's not going to escape anytime soon. And so that has actually been, some rogue person I think has tried doing that. Yeah, it's definitely something that's talked about. Solar radiation management is the one that's probably more realistic. It's cheaper, at least, to do. And so that's where you would brighten human structures, so you paint all the roofs white, or you'd plant different types of vegetation, or you cover the deserts with mirrors. And there's been a lot of studies looking at doing that and how it affects the climate. And so this one, the injecting aerosols into the upper atmosphere, is basically based on the idea of a volcanic eruption. So volcanic eruptions that we've seen in the historical period tend to lead to cooling. So Mount Pinatubo in 91 was a big enough eruption that it got into the stratosphere, and the aerosols stayed there for a couple of years, and then they reflect a lot of the sunlight, and you could see a noticeable drop of 1 to 2 degrees in the global temperatures. So there's ideas that you could just do that artificially. And then, yeah, as I was saying, there's this big Geoengineering that's looking at the impacts of that. And so you can, if you do that in a climate model, you can stabilise the temperatures. So you can, so basically you're still increasing the greenhouse gas emissions, you're offsetting that by also injecting these aerosols into the stratosphere. So you get global temperatures to be, you basically work out how much aerosol you need to inject to then offset the effect of CO2. But you can see there's still more warming over land, then it doesn't get it back to zero everywhere, right? So it's zero globally, but there's usually in these simulations there's still more warming in the Arctic than we'd otherwise have. So there's important differences in the pattern of warming that is still there. And a lot of the focus of the research has been the effects on rainfall. Because you've got this enhanced warming in the stratosphere, that then affects the stability of the atmosphere, which then has effects on the rainfall. And so there's big concerns of the rainfall changes that would still occur, plus you've got the ocean acidification that's still going on. So this isn't an ideal situation. I just wanted to finish with kind of thinking about some of the considerations, I guess, for if we decide to do this as a society. So feasibility, can we scale it large enough that it'll actually have an impact? The cost, the safety, can we do it quick enough to offset the dangerous climate effects? And can we actually get ourselves together to do it? Skip that one. So this is a nice table that talks about all the different methods that you can think of geoengineering, how it works, and then the problems. And most of them have lots of problems. So unknown side effects, the costs. If you want to remove the CO2 from the atmosphere, it can cost trillions of dollars. This one, if you're doing it from a land management perspective, it reduces the land available for crops and grazing, and we're probably going to have a problem with food production as it is, as population increases. So there's lots of things to consider. And I guess, this report of the Royal Society basically says that none of the methods offer an immediate solution. Carbon dioxide removal is preferable because it's trying to get the climate back to, it's basically trying to reverse engineer what we've done already to the climate. So it's fewer risks, but no one has come up with this carbon dioxide removal method that seems to be feasible. And they only work slowly. Solar radiation management, on the other hand, is cheaper. Only take a few years to affect climate, but there's additional risks, and I think importantly, one of the main concerns about solar radiation management is that you have to keep doing it. You have to keep injecting these aerosols into the stratosphere, or you have to keep the mirrors up there, or the umbrellas. And if that was terminated for any reason, surface temperatures would rapidly jump back to where they would have been just from the CO2 emissions, and that could have really dangerous impacts. Yeah, and I guess there's lots of ethical considerations too. So the people who are going to be doing these geoengineering things are likely to be rich, but the impacts will be likely mostly affecting poor people. And yeah, I guess we're trying to make decisions now that will affect future people, so we're making choices for the future. Is that okay? And we're also, instead of mitigating, which is going to be the best solution, we're placing these human benefits ahead of nature. So ocean acidification will keep going. The reefs will still be affected even if we're doing this solar radiation management. And the greatest challenge is really the governance. I think no one's convinced that we'll be able to do this politically and get ourselves. There's no legal sort of framework to actually be able to do that. And you can think of that in terms of wind farms. It's the same where you guys live, but in Victoria, putting up a new wind farm has huge political kind of discussions and controversy, and that's just like one little tiny small kind of region that's being impacted. So if we're doing this on a global scale, you can just imagine the negotiations. So this is just a nice cartoon sort of demonstrating that who's actually going to turn this salt shaker on to spray, this is spraying seawater into the atmosphere. And
Is that the ocean fountain? Is that what they're looking, one of the ones was a great ocean fountain? Is that,
yeah, so this was, I think, marine cloud brightening, and actually there is a proposal to do this off the coast of California. And they're going to try and do that, sort of salt spray up and brighten the clouds and see the impacts, and yeah, we'll see how that goes. I think they're still getting through all the political process to try and get that approved. But yeah, so okay, just to summarise, future warming. These are the main points I wanted to make, that future warming depends on the cumulative emissions, so the pathway, certainly for global temperature, doesn't matter, it's just the total amount of emissions. I think John Church mentioned yesterday that actually for sea level, the pathway does matter. So if you emit more now, that will have a different impact on the sea level than if you, it's not only the cumulative. But for global temperature, it's really this nice linear relationship. So limiting future climate change definitely requires substantial and sustained reductions in emissions. That was one of the headline statements of the IPCC. We are committed to additional climate change for centuries to come unless we choose to have these negative emissions. And then just, the geoengineering removal methods. So carbon dioxide removal is not really viable. Solar radiation management maybe, but the greatest challenges are probably more going to be social, ethical, legal and political rather than the scientific kind of challenge of what effects it will have and whether it can be done. Okay, thank you.
So I'm just wondering, has anyone modelled what the effects would be if we managed to sequester carbon down to like pre-industrial levels within a few decades?
So they're designing scenarios now where they're coming up with ways we could get to the 1.5 degree target, and yeah, so that's, I guess, looking at removing CO2 from the atmosphere towards the end of the 21st century, so we'll overshoot and then come back down. I'm not sure if anyone's done the scenario that you're talking about, where like a really realistic scenario where you get all the CO2. You mean in a over
to
time?
remove all the anthropogenic CO2 that we pushed out into the atmosphere, if we could manage to sequester it somehow
Yeah.
at an affordable and quick rate,
Yeah.
how long would the effects
Yeah.
take for the climate to cool?
So I guess that was one of those kind of idealised, where you go to zero emissions. So basically the constant forcing is sort of basically we're halving the amount of emissions that we have. Zero emissions is sort of, I guess, more than what you're talking about. It's kind of basically, no, yeah. So I'm not sure anyone's done it would be zero emissions from now plus removing, yeah. Yeah, I'm not sure.
Julie, with the RCP replacements, the new scenarios, do any of them, do we feed climate impact, like potential future climate impacts back into those scenarios when they're being designed? Like, do climate impacts, are they, if we think they're going to have an impact on human development in the 21st century or later, is that taken into account when designing the scenarios?
Yeah, I think they're definitely talking with each other and trying to come up with, the climate feedback onto the human systems as well, so human health, for instance. And I think ideally, when they first sat down, I guess 4 years ago now, they were hoping that they could use pattern scaling to fill out that whole matrix, so all these different social choices and how the climate influences them. But they decided that wasn't feasible. So, yeah, I think those discussions are had, but more in that integrated assessment modelling community. So they're running these simple models that try and have all of those different decisions in them and the climate feeding into them as well.
Why would the SAM change its sign after 100 or 200 years? We had this trend in the SAM index.
Oh, yeah.
And it's changing after, so if we keep moving, it's changing sign eventually.
Yeah.
What's the mechanism for that?
So that's basically, if you think about the SAM being determined by the temperature gradient from the tropics to the poles. So because the southern ocean SSTs are warming at a slower rate than the tropics, and that's true in the upper troposphere as well, the SAM trend's positive. But once these polar regions warm up, the temperature gradient reverses, and so then the SAM goes back.
What are some of the reasons for making one of the RCP scenarios higher? So I think you said the 6.01, we went to 7.
Yeah, I think it's because they wanted to have a bigger spread in the aerosols. I'm not sure of the answer. I can try and find out, but so they had to increase the final regulating forcing. But yeah, I'll have to look into that some more. I think the RCP 6 wasn't really run much anyway, and so I guess they weren't too worried about trying to have consistency from CMIP 5 to CMIP 6, where the other three scenarios, they wanted to try and keep them as similar to the CMIP 6 5 versions, so that things aren't changing too much. Yeah?
You mentioned land management as a technique to remove carbon from the atmosphere.
Yeah.
What kind of even the logic of it, but I'm having a bit trouble understanding it because I guess the point is to to increase the land carbon sink, right?
Yep.
By having more forests, I guess.
Mhm.
But you can go through as much trees as you want, and then say go back to the pre-industrial age, and that is only going to take up the carbon that was released because of land carbon change.
Mhm.
It's not going to account for the amount of carbon that is going from fossil fuels, and that's a large amount. So how that's going to help us?
Yeah, so it can't be the only solution, but it can, I guess, be a part of the solution. So there's also a lot of work, I think, in looking at soil carbon and trying to increase the amount of carbon stored in soils. But yeah, planting trees is only going to get us so far.